Okay, good morning everyone. Welcome back to ELEC3204. Hope you have all been well. Thank you for waking up on Friday morning for this lecture. um, I've received some emails from some of you. Many thanks for your emails and your questions. So I understand many of you have feel a little bit difficulty concerning coursework. The content that's related to coursework is actually provided in the slides, but it's actually in the end of my part of the course. So originally it's also a learning process to work out the coursework without detailed guidance. But I want to make your life a little bit easier. So I want to help as much as I can that is allowed by the course. So what I'm going to do today is to skip a few slides in the middle and then directly go to the final part of the slides, which is related to the coursework. How's that sound? Hopefully it will be helpful for your coursework. And if you still have difficulties in any way, by all means, send an email to me. I'll figure out what else I can do. Again, that is allowed by the course. So what I'm going to do is I will stick to slides, but I will without the board for me to write things. I will provide you with a supporting document, which is which has a few equations that's extended from the slides. They are available from the course website. I will show you a bit later. So today, first of all, we are going to talk about MIMO communication. So MIMO is multiple input, multiple output. So I have multiple antennas as a transmitter and multiple multiple receiver antennas as a receiver. So yeah, there is another thing I want to clarify, is that when you follow the equations and the concepts on the slides, let me see if yeah. So if you follow the equations and the concepts on the slides, sometimes there are inconsistencies on notations and on the definitions, but they are all correct. It happens because they are from different parts of the books that's written by the researchers in the group. But the contents are all correct. Sometimes there are inconsistencies concerning notations and the names of the concept. It happens all the time, especially in the third year now. Afterwards, you're going to, whatever you do, you're going to do a lot of reading. And then from different sources, they wouldn't use the same notation all the time. And even in the 3GPP document, which is 5G standard, many people complain that because it's the standard is written by through meeting, and then meeting the conferences, and then conferences have different meetings for different groups, different forecast groups, and yeah, there is no guarantee that there is consistency between different forecast group. But what they do is they try to, when they make an agreement on a specific area, they try to make the area as when they write about the area, they want to make it accurate and detailed as much as possible. That's what we do with slides. So there's no guarantee that there is no inconsistencies concerning the notations, but the concepts are all detailed and they are all accurate. So the supporting document I'm going to provide you, the notation will be a little bit different. I will show you in a little bit. So in here we have a memo system. Can anyone have a guess what is the biggest problem in memo communication systems? What is the biggest problem when you try to transmit signals through multiple antennas? It's probably tricky because I haven't told you yet. Any guesses? Yes, interference. So so if you transmit, so you have M transmit antennas, and then you have N receive antennas, and you transmit all these symbols, and they travel through the channel. The channel matrix is N times M. So N is the number of receive antenna, M is the number of transmit antenna. So they arrive as a receiver at the same time. So the receiver has N receive signals. So all the signals, they go through the channel together, and they arrive as a receiver together. So they will interfere with each other. So yes, absolutely, the biggest problem is interference, but there are alternative designs that where interference can be avoided. So we either try to design X here as a transmitter in order to mitigate interference, or we do more signal processing as a receiver. So we do more signal processing on Y to mitigate interference. So there are two alternatives. We either mitigate it as a transmitter, or we mitigate it as a receiver. So this is a channel matrix. We have transmit antennas and receive antennas. So that's how it looks like when it's extended. I will show more in a supporting document. So the slides, because I'm going to skip a few pages in order to get to the points that's related to the coursework. So I may not make full science at the first glance, but I'm going to show you supporting documents in a little bit. So hopefully you'll be able to follow my thinking, and if there's any problem in the way, let me know. So the first scheme that use two transmit antennas here. So we're going to talk about diversity scheme. Diversity in communication system is like when you have a received signal here, which is obtained by transmitted signal, and you have a fading element, and then you have a noise. So fading is changing, especially small scale fading is changing over time. And for a period of time, if you are in deep fade, which means the fading is quite severe over a period of time, then what you received is really weak. So you have a very small chance to recover what was transmitted. What diversity is about is if you can transmit the same signal through two channels, then if one channel is in deep fade, another one might be pretty good. So you have a higher chance of recovering what was transmitted as a receiver. So you need resource to transmit repetition of signal. So one alternative of the resource is to use multiple antennas. So if you look at the scheme here, this is the first transmit antenna and second transmit antenna. So you use two transmit antennas, and then you use two time slots. So in the first time slot, the two transmit antennas transmit X1 and then X2. In the second time slot, you transmit X1 again and then negative X2. So theoretically, originally, if you want to maximize the throughput, you can transmit X1, X2 in the first time slot, and then X3, X4 in the second time slot. So you can transmit 4 symbols over 2 transmit antennas over 2 time slots. In that way, the throughput is maximized. But for diversity, we want some repetitions. We want the receiver to be able to receive some replicas. So one design is like this. We'll see later in the supporting document that this design is this way because if I put it in a matrix, it is an orthogonal matrix, which means X. If this is a matrix, which means the Hermitian transpose of X multiplied by X equals identity matrix, or it could be a scaled version of identity matrix. So are we clear what Hermitian transpose is? Anyone tell me what Hermitian transpose is? So it's conjugate and transpose. Rows become columns, and then you take conjugate on each element. I'll show you in a little bit. I'll show you a little bit later. So as a receiver, if you only have one receiver antenna, for this example, you have what you have is so if you only have one receiver antenna, in the first time slot, you receive a signal from antenna 1, transmit antenna 1 and transmit antenna 2, go through 2 channels. And then in the second time slot, you receive signal transmitted from transmit antenna 1 and transmit antenna 2 in the second time slot, go through the 2 channels. And then you've got noise. And then with some manipulation, what we got here is, I will explain this in detail in a little bit later, but it's very important to see here that the 2 signals, after a little bit the manipulation as a receiver, so after a little bit signal processing as a receiver, the 2 signals are somehow like they are transmitted separately, and then they go through their fading channel separately, and then you receive Z1 and Z2. And Z1 is only about X1, Z2 is only about X2, so there is no interference in here at all. I will show you a little bit more about this later, so don't worry if there are gaps between these two equations. Right? So Alamoti's G2 STPC is the example in your coursework document. The transmission pattern is like this. So in the first time slot, you transmit x1 and x2 by the two transmit alternators, and then in the second time slot, you transmit x2 and x1 with some changes. So conjugate of x2 and then alter the sign for the first alternator, and then conjugate of x1. So it's designed in this way because, again, it's a orthogonal matrix, and that's how we can decouple x1, x2 as a receiver. So we do something here. There's no interference as a receiver. It's all because the transmission pattern is orthogonal. The two strings, they are kind of orthogonal to each other. When we say it's orthogonal, there is no interference. So this is what we received over the first time slot and then the second time slot, where we have the signal transmitted over two transmit alternators in the first time slot, and signal transmitted over the second time slot by the two transmit alternators. So what I'm going to do now is to show you some handwritten equations because there's no board for me to write a lot of equations. So I did them in a little bit advance. You can find them on the course website. I will show you a little bit later where to find it. Okay, so first of all, MIMO. So I have multiple transmit alternators and then multiple receive alternators. The number of transmit alternators is m, and the number of receive alternators is n. So what you received is n received signals. They are obtained from transmitting m transmit signals. And then we have this big fading matrix that kind of make the transmitted signals interfere with each other because they go through the channel at the same time and then arrive at the receiver at the same time. So if we consider a special case of using two transmit alternators and one receive alternator, what we get is, because we only have one receive alternator, here we only have one time slot, so we only receive one signal here. But we transmitted two signals, x1 and x2. And then they go through two fading elements. So what we get here is h1x1 and h2x2. So as a receiver, you only receive one signal. These two arrive at the same time. They cannot be separated. So this is called inter-alternator interference. So these two elements, they interfere with each other. So we either have to try to separate them as a receiver, or we do some design at the transmitter. So we change the transmission pattern here so that it would make it easier for the receiver to separate them. But either way, we need to separate them so that we can detect them separately. So the first diversity scheme we see in the slides is this one. So this is a page number of the slides. So for the in general, the general MIMO matrix form is this is what you transmitted. So if you have M transmit antennas, and then you transmit over T time slots, you have X of size M times T. So you transmit a total number of M times T signals. And then the fading matrix is of size N times M. You have N receive antennas. You receive signals over N antennas over T time slots. So the received signal matrix is of size N times T. So this is what you get at the beginning of your coursework document. This is a general form for MIMO. And then this diversity scheme use 2 transmit antennas and 2 time slots. The transmission pattern is you use the 2 transmit antennas. Over the first time slots, you transmit X1 and X2. And then over the second time slot, you transmit X1 and X2 again, but you alter the sign for X2. So basically, although the pattern changes for the second time slot, the information you sent out is still the same. So there is repetition between the first time slot and second time slot. We arrange it in this way because for this general form, we have X. So we have to make some arrangement for X. So the arrangement for X is like this. And this is orthogonal matrix. So X Hermitian transport multiply X will equal to identity matrix or some scale of the, yes, I will show you where you can find this document. So the received signal is, if you only have one receive antenna, then over the first time slot, you receive signal from the 2 transmit antennas over the first time slot. And then the second time slot, you receive signals transmitted from 2 transmit antennas over the second time slots here. So in general MIMO matrix form, what we get is you put y1 and y2 in this vector because you only have one receive antenna. So it's a vector, you only have one receive antenna, but 2 time slots. And then this is what you transmitted. You transmitted using 2 transmit antennas and then 2 time slots. And this is a fading matrix. You kind of map the fading, the MIMO links between the 2 transmit antennas and then 1 receive antennas. Okay, so this is a general MIMO matrix form. But what we need is here X has repetition in this matrix form. So X1 is repeated, X2 is repeated. What we want is we want a vector here. So from the receiver's point of view, you only know what you received is y1 and y2. How you model this is up to you. So you don't really know the value for x1 and x2. You know your purpose is to detect x1 and x2. So I say here is that we do this because we want to detect x1 and x2 based on y1 and y2. So this equivalent matrix form gives us a clearer view that we have x1 and x2 transmitted, and we have y1 and y2 received. This is equivalent to what happened in here. So it's only a different way of arranging the model. So as a receiver, you only see y1 and y2. But when you do signal processing, you need to model everything. So you want to model this with a purpose. The purpose is to detect x1, x2 based on y1 and y2. So here we actually arrange the fading matrix here as an orthogonal matrix. So these two are equivalent. The reason we can arrange fading matrix as an orthogonal matrix is because we arranged transmission pattern as an orthogonal transmission pattern. So it is meticulously designed. So from this step, we have a purpose for detection. Let's see how we mitigate the interference. So the trick is to use correlation operation. Correlation operation. So what is correlation operation? It is to use Hermitian transpose. So what is Hermitian transpose? It is conjugate and transpose. So rows become columns, and you take conjugate on each element. So in the previous page, we have this equivalent matrix form, y equals h, x plus noise, and they are always bar. So it's equivalent form. And we have x1 and x2 in x bar here, y1 and y2 in y bar here. So the correlation operation is to apply Hermitian matrix, Hermitian transpose of H bar to the received signal vector. So if you extend this, you see what you've got is H Hermitian transpose multiply H, and then X, and then you also apply Hermitian transpose of H to the noise. So let's ignore this one. Let's just take a look at what we get from here. So H Hermitian transpose multiply H is extended to this, and then what we get is identity scaled kind of a scaled identity matrix, because of first row, first column, we only have a complex value multiply its conjugate, so it's only power. And then first row, second column is 0 because it's H1 conjugate H2, H1 conjugate H2, but negative. So we have 0 here. So it all work out like a magic because it's orthogonal. So in the end, what we have after the correlation operation is we have Z. Here we have two Z, which are called decision variables because we are going to make decisions based on Z. Then what we get is X1 and X2. This is the channel after we do the correlation operation. This equivalent form means that equivalently we have Z1 equals to only this one multiply X1. So only here as a noise, and then Z2 equals to only this one here multiply x2. So Z2 is only about x2. Z1 is only about x1. There's no interference between them. So it is as if x1 and x2 are separately transmitted and then separately received as Z1 and Z2. There's no interference between them. And then Alamoti's STPC, this is an example you get from the slides, from the coursework website. So the transmission pattern is slightly different from what we see before. So in the first time slot, you have x1 and then x2 transmitted by two transmit antennas. And then in the second time slot, you also transmit x1 and x2, but you swap them, and then you take conjugate, and you also change the sign for x2. So we designed in this way so that the transmission pattern here is an orthogonal pattern. So as a receiver, after signal processing, there will be no interference. That is a purpose of designing the transmission pattern in this way. So the received signal, if we only have one receive antenna, we have two time slots. We receive signals like this, and then we put them in matrix. For the general MIMO form, we have this pattern for the transmit signals, and then they go through the channel, and then we receive two signals over two time slots on one transmit antenna. But we also have to model it with purpose. The purpose is to detect x1 and x2 based on y1 and y2. So what we do is we rearrange everything in here in this form so that we can see a relationship between x1 and x2 and y1 and y2. So we arrange the fading matrix as an orthogonal matrix. Everything is equivalent between step 2 and step 3 and step 4. It's only that we model them with different purposes. So here we establish the relationship between received signal and the signal that we want to detect. So now we want to do correlation operation, which is to use Hermitian transpose on the fading matrix. So if we extend this, we focus on H Hermitian transpose and then H. So this one here, because this is orthogonal. So what we get is a scaled identity matrix. It's 0 in the anti-diagonal positions. So the first line, first row, first column give us only power. First row, second column give us 0. And you get the second row in the same way. So then what we get is we get Z1 and Z2, which are called decision variables because we want to make decisions based on these two. And then X1 and X2, the fading matrix in the middle become like a scaled identity matrix. And then you get a bunch of noise here. So this is equivalent to you only transmit X1 and then get Z1. You transmit X2 and then get Z2. There's no interference between these two. So that's that works in our favor. So up to now, we only use one receiver antenna. How do we extend it to multiple receiver antenna? So it's here. So we have receive signal as n receiver antenna. So in total, we have capital N number of receiver antennas. Then in the first time slot and in the second time slot, we receive signal according to the transmission pattern. So this is a transmission pattern. And now we have total number of n receiver antennas. So the size of the fading matrix and the size of the received signal matrix is enlarged. But we have the transmission pattern is still the same. We just use more receiver antennas. So in your coursework, you have 6 receiver antennas. So the size is bigger, but you have to look at it step by step. So for the nth receiver antenna, so for each receiver antenna, you can arrange the input-output relationship like this. So you need to map the relationship between x1, x2, and y1, y2. So you receive 2 signals over 2 time slots on each antenna. So this is what you get for each antenna. And then you kind of stack them together. But the transmit matrix is still this one. So you only have x1 and x2 in this matrix. You only have x1 and x2. But you have a bigger fading matrix, and you have a bigger receiver matrix. But don't worry, what you need to do here is to do correlation. So the big H, you take the Hermitian transpose and then multiply it onto Y. So if we extend it, we need to focus on H's Hermitian matrix, multiply H. So what we get here is H Hermitian transpose and then H, because H is constituted by each individual smaller matrix. So each matrix represents the fading matrix for each receiver antenna. So now you have n receiver antennas. So if you multiply this to for each component is scaled identity matrix, and then they add together, it is a summation of scaled identity matrix. So overall, it's still scaled identity matrix. So in the end, the correlation operation give you is you get 2 decision variables, and you get 2 transmitted variables, and you have a constant here. So it is as if Z1 is only about x1, and Z2 in here is only about x2. So x bar here is here, x1, x2. And then Z here is the same as the previous page, it's Z1, Z2. But you have n receiver antenna now, so you add all the signal powers together. So let's look at where you can find this, and let's look at your coursework. Let me see. Okay. So now you see my screen. So this is a course website. In resource, so I put memo diversity here, which is a document I just showed you. You can also see memo diversity, which is your coursework is this one. Or transmit over 4 time slots. So I did give you 3 tips before. So I'm going to elaborate a little bit more in the afternoon session. So I give you 3 tips. The first tip is STPC. So the example here is only activate one user, and for the first user you only transmit using 2 antennas. So the transmission pattern is like this. You only transmit 2 transmit antennas. So the first tip is you need to search how to do STPC with 4 antennas. So the first step would be still activate only one user, but you use 4 antennas. So what we will see for the first step is you still only use one user here, but the performance would be better for the user 1. And then all the other users, they are still going to be like this because you haven't activated them yet. And the second step is activating them all, but then you will have different form of interference. We need to mitigate that interference in another way, which I will show you in the afternoon. And the third tip is error correction code. So it's up to you how far you want to go, but at least what you need to show is all the users have like waterfall, like BR, for their performance. So if I'm going to go a little bit step further, if you search space-time block code, you can see there are many sources. It's not limited to Wikipedia, but you can see here that basically this one here is the pattern for 2 transmit antennas over 2 time slots. So it's called Alamoti's code, Alamoti's space-time block code. And then if you go higher order, there are alternatives. You can either use this pattern for 4 transmit antennas, or this pattern for 4 transmit antennas, or this one here. So here you go, 3 alternatives. So what you need to do is you need to use probably this code word, or let's say it's a transmission pattern. So what it does in here is you use 4 transmit antennas, and you transmit 3 X1, X2, and X3, 3 symbols. But you kind of arrange these 3 symbols over 4 time slots, so that this matrix you see here is a orthogonal matrix. And then what you need to do is, in the supporting document, we did it step by step. So and then what you need to do is follow the same steps. So you rearrange the received signal model, and then you do correlation, so that for one user, there is no interference. What you get in the end will be Z1 for X1, Z2 for X2, and Z3 for X3. So follow the same steps, and then you use many receive antennas here. So basically follow the same steps, but the matrix would be bigger. So I'm not allowed to do that work for you. I have to stick to the slides, but I hope that's enough guidance for the first tip, which is use STPC. I will talk a little bit more about how to use multiple antennas. Multiple users in the afternoon. So yeah, see you guys in the afternoon. That's all for this session.